So hello everyone. So today we are going to learn about chain rule of derivatives, and we will start with functions of one variables and see what happens as we increase the number of variables. How is the principle of chain rule of derivatives applied? So let us start with the concept. So I'll be starting with a one variable function first, and all of us has done one variable. So suppose I have a function of one variable. Y is a function of one variable x. Okay. So when I calculate a dy by dx, it is nothing but f dash x, which is rate of change of f, rate of change of fx with respect to x. It means that what is the change that occurs in x when fx, when I increase x by 1 unit. So it is change in fx when x increases by 1 unit. So we all know standard methods of integration. For example, if my y is a function of x, which is y is equal to x square, then we know that dy by dx equals to 2x. That is the power formula. So if y is equal to x power n, dy by dx is nx n minus 1. This is simple application. I am directly differentiating y with respect to x. Now suppose y is a function of t. So y is a function of t. So suppose y is equal to t cube and t is a function of x. So let t be 2x power 7. Okay. And then if somebody asks you what is change in y with respect to x. Now we are directly not given the change in the expression for y in terms of t. So what do? We generally do if and every time it is not possible. So y is equal to t cube. So I will be substituting t as 2x power 7 cube. So 2 power cube is 8, x power 21. So my dy by dx will be 8 into 21 into x power 20. That is what my dy by dx is. So what did I do? I expressed explicitly y in terms of x. But every time it will not be possible and it will be time consuming also. So look at how we do this thing. So what I do, I first find the rate of change of y with respect to t, and then I find the rate of change of t with respect to x. Okay, so let us look at dy by dt. So this is 3t square. And what is dt by dx? So that is 2 into 14x power 6. Okay, so 3, now this is t square. So 2x7 square into 2 into 14x power 6. Okay, so it should be 3 into 4 x power 14 into 2 into 14 x power 6. Okay, so it should be 3 into 4 into 2 into 14. X power 14 into x power 6 is x power 20. Okay. Now 3 into 4 into 2 into 14. So I can write it as 3 into uh, 7 into 4 into 2 into 2. So that should be 21 into 16. Okay. And here I have 8 into 21. So there has to be an error somewhere. So let us try to do it again. So y is equal to t cube. So y is equal to 2x7 cube. So 2 cube is 8. X21 is 21. So I should be getting 21 into 8. Okay. And what is my dy by dx using the chain rule? So this is 3t square and 2 into 7. Okay, so this was 7. So that was the calculation error. Okay, so 7, 7, and 7. So my answers are now coming out to be the same. So whatever you do, you will be dealing with if a function expressed in terms of a variable, and that variable will again be expressed in terms of another variable. So whenever we are dealing with these type of questions, we are dealing with chain rule of derivatives. So we have to follow a chain. Okay. So let us do one more question. For example, if y is equal to 3s square plus 7s and s is equal to 1 upon s x, then dy by dx should be dy by ds and then multiplied by ds by dx. Now dy by ds is 6s plus 7 and ds by dx is minus 1 upon x square. And then you replace the value of s, which is this, and then you can see that it should be minus 6 upon x cube minus 7 upon x square. Let us try to do it by substitution. So y is equal to 3s square plus 7s. Put the value of s, which is 1 by x. So 3 upon x square plus 7 upon x. So this implies that y is equal to 3x power minus 2 plus 7x power minus 1. Then dy by dx will be 3 into minus 2 x की power minus 3 plus 7 into minus 1 x की power minus 2. So dy by dx is equal to minus 6 upon x cube minus 7 upon x square. So this and this are now coming out to be the same. So both the methods are going to give you the same answer, but chain rule helps us go a long way because substitution is cumbersome. It takes a lot of time. So this is called chain rule of derivatives in one variable. Now, let us try to look at functions of two variables. So now, for example, I have a function of x and y, okay? And suppose this is x square plus y square. But now x is a function of, for example, t. So x is t square and y is t power minus 1. For example, we have a situation like this. Okay. Now we have to calculate, for example, we have to calculate df by dt. So what is this? Now there's a lot of confusion. So let us see. First of all, always remember that it is a function of two variables. So if I am calculating df by dt, okay, or if I am calculating, you know, what do I say? Yes. So if I am calculating df by dt, what do I do? So you can see that f is a function of two variables, x and y. So df by dt should be, first you differentiate f with respect to x and then you differentiate x with respect to t. Please pay attention. I am using different kind of symbols. This symbol is for partial derivatives. So we know what are partial derivatives. Partial derivatives are the derivatives of multivariable functions. So if we are differentiating with respect to x, we are treating other variables are constant. Now I am using dx by dt over here because x is a function of one variable t. So we have simple differentiation. X is a function of one variable. And then we have to differentiate f with respect to y also, the partial derivative. And then y has to be differentiated with respect to t. So in that case, your del f by del t should be equal to, what is my del f by del x? 2x. I'm keeping y square as constant. So derivative of y square will be 0. What is dx by dt? 2t. Now, what is your del f by del y? So again 2y. And what is your dy by dt? Minus 1 t power minus 2. So this is my df by dt. So not del f by dt, my df by dt. This is called total derivative of f with respect to t. Total derivative means I am involving both the partial derivatives. Okay, let us try to look at a function with three variables. So for example, I have a function with three variables f of x, y, z. And suppose this is x plus y square plus z cube, where x is equal to t square, S y is equal to t and z is equal to t power minus 2. So now if I have to calculate df by dt, it should be now first I differentiate with respect to the first variable, then I do dx by dt, then I partially differentiate with respect to the second variable, then I do dy by dt, and then I differentiate with respect to the third variable and I do dz by dt. Okay. So now partial derivative with respect to x is 1, others are constant, into dx by dt is 2t, plus partial derivative with respect to y is 2y. Then I'm differentiating with respect to y with respect to t, which is 1. Partial derivative with respect to z is t power minus 2. So let's calculate with respect to z. So it should be 3z square, and dz by dt is minus 2 t power minus 3. So this is my answer. So this is called chain rule of derivatives. Okay. So now let us try to do some question from Seder and Hemant. That is the book used in Delhi University. Okay, these are the readings. So, section 16.1 of the chapter, Tools for Comparative Statics, study the chain rule of derivatives. So, I've explained you the chain rule of derivatives. So, let us try to do example number 16.1. Compute dz by dt when z is a function of xy. So, z is equal to x square plus y cube, x is equal to t square, and y is equal to 2t. So your dz by dt, now this is a function of fxy. Now look at the terminology used by the books. So I am saying del z by del x into dx by dt plus del z by del y into dy by dt. So del z by del x is nothing but del by del x of fxy. Z is your fxy. Now x is treated as the first variable. So you write f1 xy, and since I am taking the first derivative, so I'll write 1 dash. This is the terminology. Del z by del y is del by del y of fxy. So y is treated as the second variable. So f2, and I am differentiating once, so 1 dash xy. So this is very easy to remember. Okay. So whatever terminology you are comfortable with, you can use it. So now del z by del 1 is f1 prime xy dx by dt plus f2 prime xy dy by dt. Prime means derivative. Okay. So what is the partial derivative with respect to x? The partial derivative with respect to x is 2x. What is the partial derivative with respect to y? The partial derivative with respect to y is 3y square. Look at the parent expression. Okay. Now what is dx by dt? That is 2t. And what is dy by dt? That is 2. So look at this x and y. And now write the total differential with respect to t. So it is going to be 2x into 2t plus 3y square into 2. So which is 4xt plus 6y square. And now if I want everything in terms of t, so replace x by 2t. Okay, so x is nothing, x is t square, and y is 2t. Okay, so it is going to be 4t cube, 6 times 4, 24t square. So 4t cube plus 24t square. So this is my first order differential with respect to t. So that's not very difficult. And if you substitute, you can easily calculate. So let me try to substitute also and see. So what was my fxy? My fxy was x square y cube. Now what is my x square? T square whole square. What is my y cube? 2t whole cube. So I am substituting t square and 2t. So what is this? T4. What is this? 8t cube. Okay. So now my fxy is simply a function of t. So what is my df by dt? It is a function of one variable now. So this is 4t cube plus 8 into 3 t square, which is 4t cube plus 24 t square. So we are getting the same answer. Okay. All right. Let us go to the second example. Suppose two commodities are sold on a market where prices per unit are respectively P and Q. Suppose that the demand for the two commodities depend on these prices. So D1 and D2 are the demands, suppose, and demands are a function of P and Q. Okay. All other factors that might influence the demand are assumed to be constant. Remember that. So in particular, let D1 be a function of P and Q, denote the demand for the first commodity. So understood, D1 is the demand function for the first commodity. It is a function of P and Q. Suppose now these prices P and Q vary with time. So P is a function of T and Q is a function of T. Okay. Then demand can be determined as a function D1 is equal to D1 PT comma QT, of course, and a function of T alone. So remember that D1 is my demand function. My demand function was a function of P and Q. Okay. But now P is a function of T and Q is also a function of T. So my demand function is now equivalent to demand D1 PT comma QT. It means that now D1 is a function of T alone. Okay. Now, and it is interesting to ask how D1 changes with T. This problem is precisely the same as posed earlier, only the symbols are different. So now suppose you want to find d by dt of D1. So note that D1 is dependent on two variables P and Q. So I will be calculating partial derivatives with respect to P and with respect to Q. So del by del 1 of del by del P of D1 and then dP by dt plus del by d by del d1 by del q and then dp by dq by dt. Okay. So this is my formula and we can use chain rule of derivatives in economics like this. Okay. Now these dots p dot t and q dot t. So these are also standard symbol. This is d by dt of pt. Okay. And what is q dot t? This is d by dt of qt. Okay. So different symbols. You can see that here they have used these terminologies and in the initial one, they were using F1 prime and F2 prime. So whatever you are comfortable with, you can carry on with that. Okay. Let us look at example 16.3. Okay. Now suppose we have a production function y is equal to fkn. So y is a production function and production function depends on k and l, where k is the capital and l is the labor. Okay. Then obviously if I want to calculate y dot, so y dot means dy by dt. So now this t can be any variable. So I can have dy by dx, I can have dy by dy and so on. So my y dot, so suppose, so basically my dy by dt will now be del f by del k dk by dt plus del f by del l dl by dt. So dy by dt is del f by del k, k dot plus del f by del l, l dot. Okay. So this is how we deal with these kind of functions. Okay. Now in a special case of Cobb-Douglas function where fkl is a k alpha lb, we are able to get this expression. Let us see how. So if fkl is a k a l b, then del f, okay, by del k should be a k a minus 1 lb. L is a constant, only k is the variable here. So we are using power rule of derivatives. Del f by del l should be a k a b l B minus 1. So therefore, F dot should be equal to del F by del K dot plus del F by del L dot. Remember that dot means I am differentiating with respect to some variable. For example, that variable is T, and where capital K and capital L depends on some other variable T. So it can be wages or other conditions of the company. Okay. So now what is my F dot? So F dot is del F by del K, which is A, K, A minus 1 LB and K dot plus A K A B L B minus 1 L dot. Okay, so you can see that we have derived this particular condition. Okay, so now divide each term. So this is my F. So F dot and my function was Y, production function. So F dot is nothing but Y dot also. So my Y dot is equal to F dot is equal to this particular thing. So divide both sides by Y. So Y dot upon Y will be equal to A, K, A minus 1, LB, okay, K dot plus A, K, A, B, L, B minus 1, L dot, and I am dividing with A, K, A, L, B. Okay, so Y dot by Y is equal to, if we separate A, K, A minus 1, L, B, K dot upon A, K, A, L, B plus A, K, A, B, L, B minus 1, L dot upon A, K, A, L, B. So Y dot upon Y. So we can cancel the common terms. So in the first expression, we will be left with LB will cancel, A will cancel, and we will be left with A and then K dot upon K. And in the second one also, we will be left with a B and then L dot upon L. This is a beautiful expression. Okay, very easy to remember. So what is basically Y dot by Y? Y dot means rate of change divided by original. Okay, so this is nothing called relative rate of change of output. Okay, so relative rate of change of output is A times relative rate of change of capital plus B times relative rate of change of labor. So relative rate of change of production function is a linear combination of relative rates of change of labor functions and capital functions. Okay, so you can even get such a question directly to derive. And what is the idea for deriving? The idea is the chain rule of derivatives that is going to help you out. Okay, so let us look at example 16.4. Let UXZ denote the total well-being of a society, where X is an index of the total amounts of good produced and consumed, and Z is a measure of the level of pollution. So UXZ, it is the total well-being. What is X? Total amount of goods and services produced. And Z is the level of pollution. Okay, assume that UX dash XZ is positive. इस बात का मतलब क्या है? इस बात का मतलब ये है कि when X changes by 1 unit, what happens to the total well-being? So it is saying that if the number of goods are produced, which are produced and consumed okay, produced and consumed, if they increase, the total well-being also increases. This is what it means, and that is very logical to understand. इसके सिवा कुछ और नहीं होना चाहिए. Okay, and it is, they are telling you to assume that uz dash xz less than 0. This is also logical. It is saying that as the level of pollution increases, the total well-being of the society should decrease because you become unhealthy. Okay, that is also an indicator of your happiness or well-being, your health. Okay, okay, so this is positive, this is negative. Okay, now suppose the level of pollution is some increasing function of x. Now what are they saying? That level of pollution is an increasing function of x. So level of pollution is an increasing function of x. What does it mean? It means h dash x is positive. It means as as the total amounts of goods and services in an economy increase, the level of pollution increases. This is also very logical to understand. So basically, my total well-being was a function of x and z, and now z is also a function of x. So this basically becomes a function of x alone, and this is nothing but a small u, a function of x and hx. So now, because small u is representing, so basically this is same, small ux is small u x hx, so z is replaced by hx. Okay, find a necessary condition for ux to have a maximum at x equals to x star positive, and give this condition an economic interpretation. Okay, so let us start. So basically now my ux, total well-being of the society, is a function of x and hx. So I want to differentiate with respect to x now, because now it is a function of one variable. So I will be differentiating. So basically, if you see, you will be differentiating with respect to x and hx now. So you differentiate. Okay, this should be partial derivative with respect to x, and then derivative of x, plus partial derivative with respect to x, and then derivative of h. So your u dash x is ux x hx plus, because x dash is 1, plus u hx x hx into h dash x. Okay. Now, if you want to have a maxima, for maxima at x equals to x star, so whenever we want to find maxima of a one variable function, the rate of change at that particular point should be 0. इसका क्या मतलब है कि अगर इस स्टेट के बाद, if after x star, if I start increasing the number of amounts of goods which are consumed and produced in the economy even by 1 unit, my, the rate of change will decrease. The well-being of a society decreases. इसका ये मतलब होता है. तो मैक्सिमा का मतलब है कि मेरा अब रेट ऑफ चेंज 0 हो जाना चाहिए, बिकॉज इसके बाद नेगेटिव होना शुरू हो जाएगा. So I want u dash x to be 0. Okay, so what does it mean? 0 equals to ux x hx plus u hx x hx h dash x. Okay, so when I solve this particular equation, which is obtained over here also, and I'm putting this equal to 0, so I will be getting ux dash h x hx, and this is equal to minus uz dash x hx h dash x. Now all this is happening at the level of production x star. So that means I will be replacing this by x star over here, this particular point. Okay, now let us try to understand. Suppose we think of increasing x star by 1 unit. Okay, how much do we gain directly? Approximately ux dash h x x star. Obviously, this is what we told. ux dash represent the level of well-being of a society increasing when x is increasing by 1 unit. So this is the measure of how much we gain, the how much the level of well-being of a society increases when x changes by 1 unit. Okay, if we increase x star by 1 unit, level of pollution increases by about h dash x star unit. So basically this is change in well-being. Okay, this is change in pollution. Okay, for each unit increase in population, this particular quantity, we lose u dash z x star in well-being. Okay, because it is having a negative sign. So when pollution increases, the level of well-being decreases. Okay, so in all, we lose about u z dash x star h x star h dash x star from a unit increase in x star. Okay, so when I am increasing my goods produced and consumed, okay, by 1 unit, this is my level of you know uh, change in well-being, and this is my level of change in population, and this is my level of decrease in well-being. Okay, so equation start just states that what we gain directly from a unit increase in x equals what we lose indirectly through the increased pollution. Okay, so basically this is what chain rule of derivatives does. Chain rule of derivatives helps us to understand what is happening to a function of multivariables, more than one variable, when the variables are changing. And this is one classical example of what happens to well-being of a society if the well-being depends on the amount of goods produced and consumed and the level of pollution. Thank you very much.